All right, this is CS50, Harvard University's introduction to the intellectual enterprises of computer science and the arts of programming. My name is David Malin, and this is week 0. And by the end of today, you'll know not only what these light bulbs here spell, but so much more. But why don't we start first with the elephant in the room. That is artificial intelligence, which is seemingly everywhere over the past few years. And it's been said that it's going to change programming. And that's absolutely the case. It's been that way, actually, for the past several years. It's only going to get to be the case all the more. But this is an incredibly exciting time. This is actually a good thing, I do think, insofar as now using AI in any number of forms, you can ask the computer to help solve some problem for you. You can find some bug or mistake in your code. Better still, increasingly, you can tell the AI what additional features you want to add to your software. And this is huge, because even in industry for years, humans have been programming in some form for decades, building products and solutions to problems. The reality is that you and I, as humans, have long been the bottleneck. There's only so many hours in the day. There's only so many people on your team or in your company. And there's so many more bugs that you want to solve and so many more features that you want to implement. But at the same time, you still really need to understand the fundamentals. And indeed, a class like this, CS50, has never been about teaching you how to program. Like, that's actually one of the side effects of taking a class like this. But the overarching goal is to teach you how to think, how to take input and produce correct output, and how to master these and other tools. And so by the end of the semester, not only will you be acquainted with languages like Scratch, which we'll touch on today if you've not seen it already, languages like C and Python and SQL, HTML, CSS, and JavaScript, you'll be able to teach yourself new things ultimately, and ultimately be able to tell computers increasingly what it is you want it to do, but you'll still be in the driver's seat, so to speak. You'll be the pilot, you'll be the conductor, whatever your preferred metaphor is, and that's what I think is so empowering still about learning introductory material, foundational material, because you'll know what you're ultimately talking about and what you can, in fact, solve. And we've been through this before, like when calculators came out. It's still valuable, I dare say, all these years later, to still know how to do addition and subtraction and whatnot. And yet I think back on some of my own math classes. I remember learning so many darn ways in college how to take derivatives and integrals. And after like the 6th process of that, I sort of realized, OK, I get it. I get the idea. Do I really need to know this many ways? And here, too, with AI and with code, can you increasingly sort of master the ideas and then lean on a co-pilot assistant to actually help you solve those same problems. So let's do some of this ourselves here, in fact. Just to give you a teaser of what you'll be able to do yourselves before long, let me go ahead and open up a little something called Visual Studio Code, aka VS Code for short. This is popular, largely open source or free software that's used by real-world people in industry to write code. And it's essentially a text editor, similar to Notepad, if you're familiar with that, or TextEdit, kind of like Google Docs, but no bold-facing and underlining and things like that you'd find in word processing programs. And this is CS50's version thereof. We're going to introduce you to this all the more next week. But for now, let's just give you a taste of what you can do with an environment like this. So I'm going to switch over to this program already running VS Code. And in this bottom of the screen, you're going to see a so-called terminal window. Again, more on that next week. But it's in this terminal window that I can write commands that tells the computer what I want it to do. For instance, let's suppose, just for the sake of discussion, that I want to make my own chatbot, not ChatGPT or Gemini and Claude. Like, let's make our own in some sense. So I'm going to code up a program called chat.py. And you might be familiar that I am using a language here. .py, as it suggests, called Python. And if unfamiliar, you're in good company. You'll learn that, too, within a few weeks. And at the top of the file here, I can write my code. And at the bottom of the file, of the window here, I can run my code. So here's how relatively easy it is nowadays to write even your own chatbot using the AI technologies that we already have. I'm going to go ahead and type a command like import. I'm going to go ahead and type the following. From OpenAI, import OpenAI. We'll learn what this means ultimately, but what I'm going to do is write my own program on top of an API, application programming interface, that someone else provides, a big company called OpenAI, and they're providing features and functionality that now I can write code against. I'm going to create a so-called client, which is to say a program of my own that's going to use this OpenAI software. And then I'm going to go ahead and ask this software for a response, and I'm going to set that equal to client.responses.create, whatever all that means. And then inside of these parentheses, I'm going to say the following. The input I want to give to this underlying API is, quote unquote, something like, in one sentence, what is CS50? Much like I would ask ChatGPT itself. If you're familiar with things like ChatGPT and AI more generally nowadays, you know there's this thing called models, which are like statistical models that ultimately drive what the AIs can do. I'm going to go ahead and say model equals, quote unquote, GPT-5, which is the latest and greatest version, at least as of today. Now, down in my terminal window, I'm going to run a different command, Python of chat.py. And so long as I have made no typographical errors in this program, I should be able to ask OpenAI, not with ChatGPT.com, but with my own code for the answer to some question. But I want to know what the answer to that question is, so I actually want to print out that response by saying print response output text. In other words, these 10 lines, and it's not even 10 lines because a few of them are blank, I've implemented my own chatbot that at the moment is hard-coded, that is permanently configured to only answer one question for me. And let's see, with a cross of the fingers. CS50 is Harvard University's Introductory Computer Science course, the intellectual enterprises of computer science and the art of programming, weirdly familiar, covering problem-solving algorithms, data structures, and more using languages like C, Python, and SQL. OK, interesting, but let's make the program itself more dynamic. Suppose you wanted to write code that actually asks the human what their question is, because very quickly might we want to learn something more than just this one question. So up here, I'm going to go and change my code and type something like this. Type prompt equals input with parentheses. More on this another time too. But what I'm going to ask the user for is to give me an actual prompt. That is a question that I want this AI to answer. And down here, what you'll notice, even if you've never programmed before, is that I can do something somewhat intuitive insofar as line 5 is now asking the human for input. Let's just stipulate that this equal sign means store that answer in a variable called prompt, where variables, just like in math, x, y, or z. Let's go ahead and store that in prompt. So the input I want to give to OpenAI now is that actual prompt. So it's a placeholder containing whatever keystrokes the human typed in. If I now run that same command again, Python of chat.py, hit enter, cross my fingers, I'll see now dynamic prompting. So what's a question I might want to ask? Well, let's just say it again. In one sentence, in one sentence, what is CS50 question mark? Enter. And now the answer comes back as probably, roughly the same, but a little bit different, a variant thereof. But maybe we can distill this even more succinctly. How about let's run it again, Python of chat.py, and let's say in one word, what is CS50? And see if the underlying AI obliges. And after a pause, course, in a word. So that's not all that incorrect. And maybe we can have a little fun with this now. How about in one word, which is better? Maybe Harvard or Stanford? Question mark. Hope you picked right. Let's see. The answer is depends. OK. So would not, in fact, oblige. But notice what I keep doing. In this code, I keep providing a prompt as the human, like in one sentence, in one word. Well, if you want the AI to behave in a certain way, why don't we just tell the underlying system to behave in that way, so I, the human, don't have to keep asking it in one sentence, in one sentence, in one word. So we can actually introduce one other feature that you'll hear discussed in industry nowadays, which is not only a prompt from the user, which I'm going to now temporarily rename to user prompt, just to make clear it's coming from the user. I'm going to also give our what's called a system prompt by setting this equal to some standardized instructions that I want the AI to respect, like limit your answer to one sentence, quote unquote. And now, in addition to passing in as input the user prompt, I'm going to actually tell OpenAI to use these instructions coming from this other variable called system prompt. So in other words, I'm still using the same underlying service, but I'm handing it now not only what the user typed in, but also this standardized text, limit your answer to one sentence. So the human, like me, doesn't have to do that anymore. Let's now go back to my terminal, run python of chat.py once more, and this time we'll be prompted. But now I can just ask, what is CS50 question mark? And I'll likely get a correct and similar answer to before. And indeed, it's Harvard University's flagship introductory computer science course, ... So seems spot on too. But now we can have some fun with this too. And you might know that these GPTs nowadays have sort of personalities. You can make them obliged to behave in one way or another. Why don't we go into our system prompt here and say something silly like, pretend you're a cat. And now let's go back to the prompt one final time, run python of chat.py. Prompt again will be say, what is CS50? And with a final flourish of hitting enter, what do we get back? CS50 is Harvard University's introductory computer science course teaching programming, algorithms, data structures, and problem solving. And it's available free online. Meow. So that was enough to coerce this particular behavior. So this is to say that with programming, you have the ability in like 10 lines of text, not all of which you might understand yet, but that's the whole point of a class like this, to build fairly powerful things, maybe silly things like this. But in fact, it's using these same primitives that CS50 has its own virtual rubber duck. And we'll talk more about this in the weeks to come. But long story short, in the world of programming, it's kind of a thing to keep a rubber duck literally on your desk, or really any inanimate, cute object like this, because when you are struggling with some problem, some bug or mistake in your code, and you don't have a friend, a teaching assistant, a parent, or someone else who's more knowledgeable than you about code, well, you literally are encouraged in programming circles to like talk to the rubber duck. And it's through that process of just verbalizing your confusion and organizing your thoughts enough to convey it to another person, or duck in this case, that so often that proverbial light bulb goes off and you realize, I'm being an idiot. Now I hear in my own thoughts the illogic or the mistake I'm making, and you solve that problem as well. So CS50, drawing inspiration from this, will give to you a virtual duck in computer form. And in fact, among the other URLs you'll use over the course of the semester is that here, cs50.ai, which is also built into that previous URL, cs50.dev, whereby these are the AIs you can use in CS50 to solve problems, and you are encouraged to do so. As you'll see in the course's syllabus, it is not reasonable. It is not allowed to use AI-based software other than CS50's own, be it Claude, Gemini, ChatGPT, or the like, but it is reasonable and very much encouraged along the way to turn not only to humans like me, your teaching assistant, and others in the class, but to CS50's own AI-based software. And what you'll find is that this virtual duck is designed to behave as close to a good human tutor as you might expect from an actual human in the real world, knows about CS50, knows how to lead you to a solution, ideally without simply spoiling it and providing it outright. So with that said, that's sort of the end game, to be able to write code like that and more. But let's really start back at the beginning and see how we can't get from zeros and ones that computers speak all the way back to artificial intelligence. So computer science is in the name of the course, Computer Science 50. But what is that? Well, it's really just the study of information. How do you represent it? How do you process it? And very much germane to computer science is what the world calls computational thinking, which is just the application of ideas from computer science, or CS, to problems, generally in the real world. And in fact, that's ultimately, I dare say, what computer science really is. It's about problem solving. And even though we use computers, you learn how to program along the way, these are really just tools and methodologies that you can leverage to solve problems. Now, what does that mean? Well, a problem is perhaps most easily distilled into a simple picture like this. We've got some input, which is like the problem we want to solve, and the output, which is the goal we want, the solution there too. And then somewhere in the middle here is the proverbial black box, the sort of secret sauce that gets that input from output. So this then, I would say, is, in essence, is problem solving, and thus computer science. But we have to agree, especially if we're going to use devices, Macs, PCs, phones, whatever, how do we all represent information, the inputs and the outputs, in some standardized way? Is it with English? Is it with something else? Well, you all probably know, even if you're not computer people, that at the end of the day, computers somehow use zeros and ones entirely. That is their entire alphabet. And in fact, you might be familiar already with certain such systems. So the unary notation, which means you essentially use single digits, like fingers on your hand. For instance, unary, aka base 1, is something you can do on your own human hand. So for instance, with one human hand, how high can I count? All right, so hopefully 1, 2, 3, 4, 5. And if you want to count to 6 and to 11 and 10 and so forth, you need to, take out another hand or your toes or the like, because it's fairly limiting. But if I think a little harder, instead of just using unary, what if I use a different system instead? What about something like binary? Well, how high, if you think a little harder, can you count on one human hand? So 31, says someone who studied computer science before. But why is that? It's kind of hard to imagine, right? Because 1, 2, 3, 4, 5 seems to be the 5 possible patterns. But that's only when you're looking at the totality of fingers that are actually up. 5 in total, or 4 in total, or 1, or the like. But what if we take into account the pattern of fingers that are up, and we just standardize what each of those fingers represent? So maybe we all agree, like a good computer would too, that maybe no fingers up means the number 0. And if we want to count to 1, let's go with the obvious. This is now 1. But instead of 2 being this, which was my first instinct, maybe 2 can just be this, a single second finger up like this. And that means we could now use 2 fingers up to represent 3, I'll propose. We can use just 1 middle finger up to offend everyone, but represent 4. I could maybe use these 2 fingers with some difficulty to represent 5, 6, 7. I'm already up to 7, having used only 3 fingers. And in fact, if we keep going higher and higher, I bet I can get as high as 31 for 32 possible combinations. But the first one was 0, so that's as high as we can count. So we'll make this connection in just a moment. But what I started to do there is something called base 2. Instead of just having fingers up or fingers down, I'm taking into account the positions of those fingers and giving meaning to like this finger here, this finger here, this finger here, and so forth. Different weights, if you will. So the binary system is indeed all computers understand. And you might be familiar with some terminology here. Binary digit is not really something anyone really says, but the shorthand for that is going to be bit. So if you've heard of bits, and we'll soon see bytes, and then kilobytes and megabytes and gigabytes and terabytes and more, this just refers to a bit, meaning a single binary digit, either a 0 or a 1. A 0 is perhaps most simply represented by just like turning, maybe keeping a finger down, or in the world of computers, which have access to electricity, be it from the wall or maybe a battery, you know what we could do? We could just decide sort of universally that when a light bulb is off, that thing represents a 0. And when the light bulb is on, that thing's going to represent a 1 instead. Now, why is this? Well, electricity is such a simple thing, right? It's either flowing or it's not. And we don't even have to therefore worry about how much of it is flowing. And if you vaguely remember a little bit about voltage, we can sort of be like 0 volts. Nothing's there available for us. Or maybe it's 5 volts or something else in between. But what's nice about binary, only using 0s and 1s, is that it maps really nicely to the real world by like throwing a light switch on and off. You can represent information by just using a little bit of electricity or the lack thereof. So what do I mean by this? Well, suppose we want to start counting using binary, 0s and 1s only. Well, let's think of them metaphorically as like akin to these light bulbs here. And in fact, let me grab a few of these light bulbs, and let me propose that if we want to represent the number 0, well, it stands to reason that here, single light bulb that is off can be agreed upon as representing 0. Now, in practice, computers don't have little light bulbs inside, but they do have little switches inside. Millions of tiny little things called transistors that, if turned on, can allow it to capture a little bit of electricity and effectively turn on a metaphorical bulb. Or the switch can go off. The transistor can go off and therefore let the electricity dissipate, and you have just now a 0. Unfortunately, even though I can let some electricity, here's the battery I mentioned is required. Even though we might have some electricity available to us, I can therefore count to 1. But how do I go about counting? Hardware problem. How do I go about counting higher than 1 with just a light bulb? Yeah, so I need more of them. So let me grab another one here. And now I could put it next to it. And this, too, I'll claim is just still the number 1. But if I want to turn 2 of them on, well, that would mean I could count to 2. And if I maybe grab another one, now I can count as high as 3. But wait a minute. I'm doing something wrong. Because with 3 human fingers, how high was I able to count? So 7 in total, starting at 0. So I've done something wrong here, but let me be a little more clever then about the pattern that I'm actually using. Perhaps this can still be 1, but just like my finger went up and only one finger in the second version of this, this can be what we represent as 2. Which one do I want to turn on as 3? Your left or your right? So you're right, because now this matches what I was doing with my fingers a moment ago, and I claimed we could represent 3 like this. If we want to represent 4, that's fine. We have to turn that off, and this on, and that's somehow 4. And let's go all the way up to 7. Which ones need to be on to represent the number 7? All right, so all of them here. Now, if you're not among those who just sort of naturally said all of them, like what the heck is going on? How do half the people in this room know what these patterns are supposed to be? Well, maybe you're remembering what I did with my fingers, but it turns out you're already pretty familiar with systems like this, even if you might not have put a name to it. So in the human world, the real world, most of us deal every day with the so-called base 10 system, otherwise known as decimal, dec implying 10, because in the decimal system, you have 10 digits available to you, 0 through 9. In the binary system, we only had 2, bi implying 2, so 0 and 1. And unary, we had just 1, a single digit there or not. So in the decimal system, we just have more of a vocabulary to play with. And yet, you and I have been doing this since grade school. So this is obviously the number 123. But why? It's technically just 3 symbols, 1, 2, 3. But most of us, your mind immediately goes, OK, 123. Pretty obvious, pretty natural. But at some point, you, like me, were probably taught that this is the ones place, and this is the tens place, and this is the 100s place, and so forth. And the reason that this pattern of symbols 1, 2, 3 is 123 is that we're all doing some quick mental math and realizing, well, that's 100 times 1 plus 10 times 2 plus 1 times 3. Oh, OK, there's how we get 100 plus 20 plus 3 gives us the number we all know mathematically is 123. Well, it turns out whether you're using decimal or binary or other base systems that we'll talk about later in the course, the system is still fundamentally the same. Let's kind of generalize this away. Here's a 3-digit number in some base system, specifically in decimal. And I know that only because of the placeholders that I've got on top of each of these numbers. But if we do a little bit of math here, 1, 10, 100, 1,000, 10,000, and so forth, what's the pattern? Well, technically, this is 10 to the 0. 10 to the 1, 10 to the 2, and so forth. And we're using 10 because we can use as many as 10 digits under each of those columns. But if we take some of those digits away and go from decimal down to binary, the motivation being it's way easier for a computer to distinguish electricity being on or off than coming up with like 10 unique levels of electricity to distinguish among. You could do it. It would be annoying and difficult to build in hardware. You could do it. So much simpler to just say on and off. It's a nice, simple world that way. So let's change the base from 10 to 2. And what does this get us? Well, if we now undo the math, that's 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. So the mental math is now about to be the same, but the columns represent something a little bit different. So for instance, if I turn all of these off again, such that I've got off, 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 otherwise known as 0, 0, 0. It's 0 because it's 4 times 0 plus 2 times 0 plus 1 times 0 still gives me 0. By contrast, if I turn on maybe just this one all the way over on the left, well, that's 4 times 1. Because on represents 1 and off represents 0, plus 2 times 0 plus 1 times 0, that gives me 4. And if I turn both of these on, such that all 3 of them are now on, aka 1, 1, 1, that's 4 times 1 plus 2 times 1 plus 1 times 1. That then gives me 7. And we can keep adding more and more bits to this. In fact, if we go all the way up numerically, here's how we would represent in binary the number you and I know as 0. Here's how we would represent 1. Here's how we would represent 2 and 3 and 4 and 5. And you can kind of see in your mind's eye now, because I only have 0s and 1s and no 2s or 3s, not to mention 9s, I'm essentially going to be carrying a 1 in a moment if we were to be doing some math. So to go from 5 to 6, that's why the 1 ends up in the middle column. To go to 7 here gives us now 1, 1, 1, or on. How do I represent 8? Using 1s and 0s. Yeah? Yeah, so we're going to need to add another digit. We need to throw hardware at the problem using an additional digit so that we actually have a column representing 8. Now, as an aside, and we'll talk about this before long, if you don't have an additional digit available, if your computer doesn't have enough memory, so to speak, you might accidentally count from 0, 1, 2, 3, 4, 5, 6, 7, and then accidentally end up back at 0. Because if there's no room to store the 4th bit, well, all you have is part of the number. And this is going to create all sorts of problems then, ultimately, in the real world. So let me go ahead and put these back and propose that we have a system now, if you agree to sort of count numbers in this way, via which we can represent information in some standard way, and all the device underneath the hood needs is a bit of electricity to make this work. It's got to be able to turn things on, aka use some transistors, and it's got to be able to turn those things off so as to represent zeros instead of ones.
Welcome everyone, and especially those of you kicking off your Introduction to Computer Science journey. Let's jump right into this explainer on how we actually keep track of data. We're going to go all the way from ancient sheep counters right down to the modern computer memory sitting inside the device you're using right now.
Okay, so we'll trace this evolution through 4 quick steps: the origins of counting, the decimal system, binary and hardware, and finally, hexadecimal memory.
Right, let's kick things off with part 1, the origins of counting.
To really understand computer memory, we actually need to look at a fundamental historical challenge, and that is, how do we keep track of our stuff? Before mathematics as we know it even existed, early humans needed a physical way to represent their property. I mean, if you had a massive flock of sheep, you couldn't exactly just save a spreadsheet to the cloud, right? You needed a tangible, reliable way to know exactly what you owned.
Early humans solved this in a really simple way. They just used scratch marks. One scratch equaled one sheep. But as those flocks grew, counting individual marks got incredibly tedious. So they evolved. They started grouping those scratches into tallies to make counting to numbers like 24 recognizable at just a glance. Think of it as our very first data compression algorithm.
Moving right along to part 2, the decimal system. As civilizations evolved, so did their counting methods. Different cultures developed all sorts of ways to count, but a massive breakthrough happened when the Arab people borrowed a numbering system from India. This system introduced something entirely revolutionary: the number 0. Now, a 0 wasn't strictly necessary for counting rocks or sheep. You either have a rock or you don't. But adding the concept of 0, that became absolutely crucial for scaling up our mathematics.
This base 10 system uses 10 unique digits, 0 through 9. Think of it kind of like an odometer on a car. When we count up and run out of digits at 9, how do we represent the next sheep? Well, we solve it by resetting the dial back to 0 and adding a new place value digit to the left, which represents one group of 10. That gives us 10, then 11, then 12, and so on. So our entire understanding of math is basically built on this base 10 odometer rolling over.
Which brings us to part 3, binary and computer hardware. And for the Intro to CS students out there, this is where you really want to pay attention.
So, what happens when the hardware doing the counting isn't a human brain, but a machine? Computers don't have 10 fingers to count on. They are completely constrained by their physical hardware, specifically these microscopic transistors. A transistor can really only identify one thing, whether electricity is present or not. No electricity? That's a 0. Electricity is present? That's a 1. And this strict hardware limitation forces a complete shift away from our 10-digit decimal system down to a 2-digit system we call binary.
Using that odometer metaphor again, let's try counting in base 2. We start with 0, then 1. But wait, we're already out of digits. So we add a place value to the left that represents a group of 2, giving us 10 and then 11. Now we're out of 2-digit numbers. We have to add another place value. But in base 2, the next place value is 2 times 2, which is 4. So we write 100. That binary number 100 actually represents exactly one group of 4s, 0 groups of 2s, and 0 groups of 1s. It equals the decimal number 4. Now, when we compare standard base 10 decimals to their binary equivalents, a glaring problem emerges. Binary numbers get much longer, incredibly fast. While the decimal number 4 is just a single digit, it already takes 3 digits in binary. By the time we count up to 24, we're using 5 binary digits. The math is perfectly accurate, for sure, but it eats up a massive amount of physical space in the hardware.
And that rapid expansion perfectly sets up Part 4, hexadecimal and memory space.
You see, if every tiny number takes up so much physical space in memory, you're going to run out of RAM really quickly. Decades ago, engineers needed a way to represent larger numbers using fewer place values just to save that precious limited memory. A perfect modern example of this space-saving trick is the MAC address on your smartphone. For your device to be found on the internet, it needs a unique identifier. To keep that identifier super compact, engineers decided to use base 16, which is known as hexadecimal.
But wait, how do you count in base 16 when humanity only invented 10 numbers? Well, it's pretty simple, actually. We just added letters. The base 16 digits go from 0 to 9, and then we use A for 10, B for 11, C, D, E, all the way up to F for 15. This means our hexadecimal odometer doesn't run out of single digits, and it doesn't add a new place value until it actually hits the letter F.
Just look at how efficiently base 16 compresses data. To write the number 15 in base 10 takes 2 digits. In binary, it stretches all the way out to 4 separate digits, 1, 1, 1, 1. But in hexadecimal, it's just a single character, the letter F. It is a ridiculously elegant solution for strict hardware constraints.
And this brilliantly illustrates why hexadecimal is just so powerful for computer science. Take the largest 12-digit hexadecimal number you can write, 12 Fs in a row. The equivalent decimal number is over 281 trillion. That's a massive 15-digit number. Hexadecimal perfectly shrinks a 15-digit decimal requirement down to a 12-digit hex number. When early computer memory space was highly limited, saving 3 digits of space per large number was a monumental deal.
So we've journeyed from scratching rocks to base 10 and seen how base 2 and base 16 were invented purely to solve the physical hardware constraints inside our machines, which sets up the ultimate question for your continued computer science journey. How do all these raw physical electrical signals, these literal zeros, ones, and letters, actually translate into the video games, apps, and software you use every single day? Well, that is exactly what you'll be diving into next. Catch you later.